Hello. I didn't see you come in there. So chemists, today we're going to talk about catalysts. Now, our learning goal here is to be able to predict the impact of a catalyst on the energy profile of a reaction. We're also going to talk a bit about, with an example, catalyst in biology and industry. This is our vocabulary for the lesson. If I could just get you to pause the video here and write this down. Some of this will be new to you, some of it won't be new to you, and yeah, that way you'll have it to refer back to as we move forward through the lesson. So catalysts, it's not just a list of all the cows that you own. Basically, catalysts break bonds or form intermediary compounds, both of those are true, and these allow new compounds or new bonds to be made. So basically what they're doing is they're modifying the transition state. Now the transition state is the position in the reaction coordinate, where both the orientation and the energy of the particles means that they are likely to react. So this allows the chemical reactions to occur. Now, just because chemistry is a bit of a spectrum, there'll be a very, very small amount of reactions that happen beforehand, and so before you achieve the activation energy. There'll still be a small amount of reactions taking place. So catalysts, in other words, they make reactions more likely to occur. And what we see over here is we have our particles A and B, and they're not joined together, but they're going to form an intermediary compound with the catalyst and then move on from there. And we see now they're bonded together. That intermediary compound makes it easier for that reaction to occur in the first place. If we run this animation backwards, which I don't know how to do, but if we did, what we would see is this compound would bond here and then break apart. So thus, breaking to form new bonds. Now, the activation energy decreases, but the enthalpy is constant. A catalyst will have no effect at all on the overall enthalpy of a reaction. Remember, enthalpy is a state-dependent function. In other words, it only depends on what the reaction was, what the states were at the beginning of the reaction and at the end of the reaction of all the species, and that's how that determines a change in enthalpy for a reaction. So, catalysts do increase the rate of reaction. They do not get used up in the reaction, so they're present at both ends. They do reduce the activation energy, and they do not affect the enthalpy. So catalysts and biology. So catalysts in biology and industry, right? Basically, many biochemical reactions occur at a really low temperature, around 25 to 40 degrees. That's really low for chemistry. We tend to call a moderate reaction between 500 to 1,000 degrees Celsius. So like that's about 790 to 1290 Kelvin. So that's a moderate temperature. High is above 1500. So the activation energy is unlikely to be achieved without a catalyst, in this case enzymes, in many reactions. So for example, the production of sugar in photosynthesis, we need the enzyme from chlorophyll, right? We need the enzyme chlorophyll. And chlorophyll allows this reaction to happen at low temperatures during the daytime. And we see what happens here. The enzyme bonds with the substrate. The substrate is the reaction, or the substance which is occurring, the reaction is occurring to, and we call it substrate in biology. And because it's here, it's able to happen at a lower, it's bound there, so it's able to happen at a lower temperature, and then we get a product. And this tends to be considered a lock and key model, which works. I mean, it's not 1,000% accurate or 100% accurate, but it works. And over here in industry, we use catalysts for lots of reasons. One's to lower the production costs, to increase safety, and increase the yield. Because, for an example, an exothermic reaction in equilibrium, if we increase the temperature, we will produce less products and more reactants. So if we have a catalyst, that means we can do it at a lower temperature. The good common example that we'll use in our course is the Haber process. And that is where we go from ammonia and hydrogen to over a catalyst of iron oxide to produce ammonia plus heat. Now, the heat here means it's an exothermic reaction, but we're using iron oxide. The transition metals in general are really common sources of catalysts in industry. They work really well for a lot of reactions. Remember, as I said, this is an exothermic reaction, and you can see here with our arrows, double arrows, that it's in equilibrium. So excess heat actually drives it this way, and that reduces the yield. So if we use a catalyst, we can make this reaction occur at a lower temperature. All right, I hope that made sense. If it didn't, put any questions you have in the comments below, and we'll get back. Thank you for watching. Don't forget to subscribe so you can keep up with all of our excellent science content we're putting out there. And yeah, we'll see you next time. Bye now.